Okay, so then let's come to the next speaker. Do you want to share your screen already?
Yes. Okay. Wait on. So I think you already see the slides. Okay, everything
perfect.
works.
Yeah, so yeah, welcome to our second talk. And our next speaker is Ludovico Lami from University of Ulm. And he will tell us about entangleability of cones. So go ahead.
Okay. Well, first of all, let me thank the organizers for giving me this great opportunity. I'm really grateful. And also my great, fantastic co-authors, Guillaume Aubrun, Carlos Palazuelos, and Martin Plávala, without whom this work would have never been possible, and especially Guillaume Aubrun for really being instrumental in devising the proof and some crucial steps there. So that's first take-home message of the talk is Guillaume Aubrun is a great mathematician and great person. Okay, right. So let's dive right in. So with a bit of a philosophical introduction. So I guess the first interesting lecture that you take in a quantum mechanics course is superposition is a real thing, is a property of the physical world, right? Basically the double slit experiment. Okay, and the second interesting lecture in quantum mechanics is by superimposing product states, one obtains entangled states. So, so entanglement is also a physical phenomenon. And these two fundamental notions are somehow connected by a kind of accidental feature, if you want, of the quantum formalism. So the fact that, of course, like in a tensor product space, not all vectors are of tensor product form. And so we are allowed to deduce the existence of entanglement from that of superpositions only if we believe in the mathematical structure of quantum theory. Okay, but we know that quantum theory may not be the ultimate theory of nature, so that we want to understand what happens to this relation between superposition and entanglement for other possibly non-quantum or post-quantum, if you want, theories. And our results fill exactly this gap. And okay, modulo some non-trivial assumptions that I will explain kind of establishes, if you want, a universal connection between these two fundamental notions of superposition and entanglement. And we kind of show that they logically imply one another. Okay, so there's a bit of a vague claim. I will make it mathematically precise later, but this is kind of the main philosophy. Okay, so I mean, as I said, we have to go beyond quantum first. So how can we systematically construct more general theories? Okay, so there are two fundamental notions when you design a physical theory. One is the notion of state, which is just a physical system together with a preparation procedure. So really kind of a list of things you should do to prepare your system in some initial configuration. And the other fundamental notion is that of effect. So an effect is just a measurement device together with one of its possible outcomes. So you can really like a measurement apparatus with the blueprint plus something that could appear on its display. Really, that's really what it is. And the theory for us, very minimal assumption or theory, is just there is a rule that assigns to every pair of states and effects a probability P. Okay, so that's a theory. That's really I mean, we know that from quantum mechanics, we cannot expect a theory to be fully deterministic. So to have, predict something with certainty, but at least the probability, we want to retrieve it. Okay, so this is kind of a systematic introduction to GPTs. This is my PhD thesis. And recently there was also this nice overview by Markus Müller. I also recommend it. Okay, so let's start by looking at quantum theory from a bit of a more general perspective. So as a GPT, so you have the cone of anomalized states. This is just the cone of positive semi-definite matrices. So we call it PSD. It lives in the space, the real space of n times n Hermitian matrices. Great. So then what you do is you take a trace, you take the functional trace, and you look for those states that have in the cone that have trace 1. So basically you cut a slice of this cone at height trace equal to 1. So trace is a functional on the state space, and it kind of cuts through the cone and defines a state space. What are the effects? Well, there are elements of P of EMs in standard quantum theory. So there are matrices between 0 and 1 in the positive semi-definite order. So if you look at the picture on the right-hand side, you have the space of Hermitian matrices, you have the identity up there, the 0 here, and then you take this kind of figure, all the matrices that are larger than 0 and less than 1. Okay, and then you have the Born rule. If you want to compute the probability of an effect being recorded on a state row, you have just to take the trace of the product. Okay, so this is a probability. It's a valid number between 0 and 1. Okay, so GPTs are basically the same. I will reuse the same drawings, but now the cone of states is just any convex cone, okay? Any proper convex cone. I'm not going to define what I mean by proper, but it's because it's super intuitive, just a reasonable cone. So it means that it doesn't shrink to a line in any direction. So it's kind of full dimensional, and it doesn't also open up to have to contain a straight line in any other direction. Okay, so and once you have this cone that lives in any finite dimensional real vector space, you can normalize the states. So you can consider a strictly positive functional U, and so that will be exactly a functional, a linear functional on the state space, and we require the strictly positive means that it really the hyperplane that it defines cuts through the cone C. So it kind of doesn't graze it, it really cuts through it. What are the effects? Well, for the effects, we need to go to the dual space, and we need to look at the dual cone. The dual cone is just a cone of functionals on V that are positive or everywhere non-negative on C. Okay, fantastic. So the effects are all those functionals that are between 0 and the unit, the normalizing unit, in this ordering defined by this cone C star. And then you have the generalized Born rule. The generalized Born rule tells you that if you want to compute the probability of an effect E being recorded on a state omega, you just have to evaluate the functional E on the state omega. And since E is between 0 and the other unit, this number will be between 0 and 1. Okay, I'm going to make the first non-trivial assumption here, which is the no restriction hypothesis, which is that this it tells you that all mathematically reasonable effects, that means all functionals in this set over here, they are physically implementable. Okay, so they correspond to actual physical preparation procedures. Okay, this is a non-trivial assumption. It turns out to hold in quantum mechanics and in classical probability theory, which is one of the reasons why we deem it reasonable, and also because it leads to a neat mathematical problem. But it's an assumption. Okay, so let's give the first simple example of a GPT, which is classical theory. What is classical theory? So you just pick any real vector space, you pick any basis of it, and you define the cone of positive or non-negative linear combinations of those vectors in the base. And as a unit functional U, you take any functional that is strictly positive on all states, on all vectors in the spaces. Okay, this defines a classical GPT. That's a picture, right? So you take so in three-dimensional space, you take three vectors, and okay, this cone, this kind of triangular based cone that you get is a classical cone, and you cut through it with a unit functional, and that defines your state space, which in this case would be a triangle in higher dimensional simplex. Okay, so just to summarize, a classical cone is just a cone generated by a basis of its vector space. Okay, and note that the cone is classical if and only if its dual is classical. So if you look at the dual of this cone will be another triangular-based cone, so the classical cone, and it turns out to be generated by the dual basis of this one. Okay, so that's very good because classicality, so it's a notion that is somehow invariant under duality. Okay, and this notion of non-classicality or of classicality, of not being classical, it's what we will take as a definition of superposition for general probabilistic theories. Why? Because superposition, as is defined in a standard way, it really requires a Hilbert space structure. So in GPTs, we don't have a Hilbert space structure because there is no underlying Hilbert space. So what we do have is just notion of convex mixtures. So we say that a theory is non-classical if and only if there are states that are not generated by convex mixtures of a fixed finite set of states. And this is exactly the case in quantum theory. Okay, so we have to talk about bipartite systems. So you have two GPTs. How do we describe the bipartite system? Well, with another GPT. here comes the second assumption that I'm going to make, which is the local tomography principle, that tells you that global states are uniquely determined by their statistics under local measurements. Okay, and that's a non-trivial assumption. Once again, it holds in quantum mechanics, it turns out, and also in classical probability theory. So it is in a way a reasonable assumption. And it also leads to a neat mathematical problem. That's why it also can be deemed reasonable. But it basically tells you that there are no more degrees of freedom in the bipartite system that there were in the local systems. Okay, so there may be more states, but not more degrees of freedom. Okay, so the good news is that with this assumption, we can uniquely establish that this vector space over here is just a tensor product of the two original vector spaces, and the same for the other unit. That's normalizing functional. So what can we say about the third element of the triple, which is the cone? Well, okay, the first thing we should say is that separable states should be in it, right? Because we should be able to prepare separable states in a bipartite system. So that's the convex hull of this set of product unnormalized states should be really in the cone. And the second thing is the dual of this. So if you take the set of separable measurements, separable effects, they should be in the dual cone because they should be valid measurements. Separable effects should be applicable by spatially separated observers. Okay, so I can take the dual of this cone here, and I denote this with this weird symbol. So I call this the minimal tensor product of the two cones, CA and CB, and this is the maximal tensor product of the two cones, CA and CB. Okay, just quick summary. All we can say for now is that the minimal tensor product, so the cone of separable states, must lie inside the cone CAB, and the maximal tensor product, so the dual of the maximal tensor product, that is the minimal tensor product of the cone of the dual cones, should lie inside the dual cone. Okay, just another quick exercise. You can take the dual of this inclusion, and you will get an upper bound on CAB, because taking the dual reverses the sign of this inclusion, so you get kind of an upper bound for CAB as the maximal tensor product. Okay, great. So the crucial observation for us is that if the minimal and the maximal tensor product are different, that means that one of these two inclusions is strict. So they cannot be both saturated if this and this are different. And that also means that either this inclusion is strict, so it's not saturated. That means that there are entangled states, or the other inclusion over here is not saturated. So that is, there are entangled measurements. Okay, so basically the cone CAB has disappeared now, and we have been able to conclude something about the cone, that is, that there are either entangled states or entangled measurements, provided that this hypothesis holds. Okay, so this is the main problem. When does it hold? When is it that the minimal tensor product and the maximal tensor product are not the same? And we signify this by calling the two cones entangleable. Okay, the simple observation is that if either CA or CB is classical, then CA and CB are not entangleable. Okay, that is physically reasonable because if your GPT is classical, then of course you cannot support entanglement with any other GPT. It is less trivial to show that a GPT, well, a cone is classical if and only if it is not entangleable with all cones. So basically, this was proven by Lami and Phelps. If you have a cone and this happens to be not entangleable with any other cone, then that means that the cone is classical. And okay, that's a nice result, and it's in fact it's stronger. What Lami and Phelps prove, it's stronger than this in the sense that it suffices to test one single cone CB instead of possibly an infinite family of them. So that's very nice, but it's not physically satisfying because it's not that we can test any cone we want, right, or any specific cone. I mean, our physical theory will tell us what kind of cones we have available. And it's not that we can come up with examples and try and test them. So luckily enough, there is another conjecture by Barker that was put forward in the 70s, mid-70s. that is that two cones are entangleable if and only if neither of them is classical. Okay, so that's very strong, and this is actually physically interesting because now, I mean, we are given the two cones, and we can test their entangleability based on their non-classicality, and we don't have to vary over the cone CB. It's just for any two cones. Okay, so the main theorem that we prove is the solution of Barker's conjecture, so that the two cones are entangleable if and only if neither of them is classical. Okay, so just to go back to the initial picture, this establishes kind of a universal, if you want, connection between entangleability and superposition and non-classicality. So, and the fact that these two notions that are, one is local, superposition or non-classicality, and the other is global, entangleability, the fact that they are intimately connected is really, I mean, to me, it's really aesthetically pleasing and really somewhat surprising. So that's it's a nice connection. It's really beautiful to me. Okay, there is an immediate reformulation of this theorem that tells you that well, if you have two cones and you want to consider all positive maps between them, there will be some that are not measure and prepare if one of them, basically none of them is classical. Okay, so that in other words, that you have that all positive maps are measure and prepare if and only if either CA or CB is classical. Okay, so if you have two non-classical theories and you try to consider a set of transformations, some of them will not be measure and prepare, which is something we know in quantum mechanics. And this also solves a conjecture in the theory of abstract operator systems, which is concerned with minimal and maximal tensor product of arbitrary cones with the cone of positive semi-definite matrices. And they were asking whether the minimal and maximal tensor product can be the same for any n, and the answer is if and only if C is classical, exactly by our theorem A. Okay, so just to say that this has well, applications in other fields of mathematics, and indeed, I mean, the motivation by Barker came from the theory of order vector spaces, and so it had nothing to do with GPTs. Okay, so last minute, just 8 minutes, I guess, we give an overview of the proof. Right. So, I mean, the easy part is to prove that if they are entangleable, but neither of them is classical, right? Because if one is classical, then it cannot be entanglement. So this is relatively easy, and it's been long known. The opposite implication is much harder. So you have two cones, neither of them is classical. You have to construct to come up with an entangled state. That's not easy. So, and we have two main tools. One is what we dub the Kite square sandwiching of cones. So that is, we reduce the problem to a basically an integrability problem, slightly modified for two special three-dimensional cones that we choose carefully. And then the second part is we exhibit an entangled state for this three-dimensional problem by a brute force construction. Okay, so that's kind of our strategy. Okay, so let's start with the Kite square sandwiching. Consider this following two-dimensional shapes. So you have the unit square. You pick basically 4 points on the 4 edges, but not on the corners, and you look at the convex hull. So this would be our kite, d alpha, and our blunt square is just the same unit square without its corners. Okay, so that's why it's blunt. Okay, and the last thing you have to do is you have to construct the three-dimensional cones with that base. Okay, so based on the kite and on the blunt square. And you do this by just appending to any two-dimensional vector that belongs to any of that set. You append the coordinate 1, right? So you kind of you hang this set at height 1, and then you consider the cone generated by it. If it is a three-dimensional cone, it's a perfectly valid construction. Of course, the cone generated by the blunt square will not be closed because they are the missing kind of extremal rays, but it is still very useful, as we will see. And our definition of Kite square sandwiching is the following. So it's a sandwich. So we have a general cone in a general vector space, and we want to somehow relate it to the kite and the blunt square. So there are two main tools. One is the lift map. It's a linear map that goes from R3 where the kite and blunt square live, to V, and the other is a compressed map that goes from V to R3. And you require the product of them to be the identity on R3. Of course, I mean, the other composition could not be the identity because of rank constraints, because V could be very large. But this composition can be the identity on R3. And you require then when you lift the kite cone, you end up within the cone C. And when you compress the cone C, you end up within the blunt square cone. Okay, so the theorem, really important theorem that we prove, important for the proof, is that a cone is non-classical if and only if it admits a chi-square sandwiching. Okay, and this is really the geometrically hard part of the paper that requires some tools in convex geometry that are to be very sophisticated. Okay, and this the proof takes up basically almost a half of the paper, and this is really largely Guillaume's merit. So I want to stress this. Really a non-trivial part of the proof is this. Okay, but we're going to take this for granted. Sorry, Guillaume, because I mean it's really too long to explain, and I'm not the right person to do it. But we focus on the next question, which is how does this help? Theorem B. Well, suppose we prove that the following crucial fact. Okay, intuition will follow. So suppose that you have two possible parameters for the kites, and okay, and I claim that there is a tensor that is in the maximal tensor product of the kites, but is not in the minimal tensor product of the blunt squares. Okay, and then we are done. Why is that? The short answer is that we use theorem B and the lift and compress maps to transform omega basically into an entangled state of the big cones. This is an entangled state of the three-dimensional cones, right? So the small cones. But with the lift maps, we kind of transform it into an entangled state. We check that it's entangled using the compress map, basically. So that's you need both lift and compress. Okay, so I mean, okay, this is the proof of what I said, just in formula. It's not complicated, but okay, maybe not so useful to go through it, but it's really simple. Okay, so so the intuition behind this proposition is that in spite of the kites being significantly smaller than the blunt squares, right, because they are geometrically smaller, they give rise to enough entanglement to actually stick out of the minimal tensor product of the blunt squares. The blunt squares is a big set, right? So the minimal tensor product is still big, but they give rise to enough entanglement to actually stick out of this. That's the intuition. But how do we prove it? Well, with a brute force approach. That's where the brute force comes into play. So you have 4 extreme points for each kite. Okay, it's nothing deep. I just wrote them down. We scale them so that this nice sum rules are obeyed. This is possible because the 2 diagonals of kites meet in a single point. So actually, this rescaling coefficients are basically uniquely defined up to a multiple. And then we construct this state omega of this somehow CHSH flavor. You see, like there are 4 product states, right? They are all with a plus, but this one is with a minus. Okay? So if this were also a plus, this would be a separable state because there will be 4 pluses, but it has a minus, so that's enough to kick it out of the separable cone, so the minimal tensor product, and but it's still in the maximal tensor product. And that's actually easy to verify. And how do we prove that this is not in the minimal tensor product of the blunt squares, so that it really sticks out a lot? We introduce a witness. Okay, and this is the witness we choose. It's kind of, there are 2 pieces. One is basically the normalization, and the other is a CHSH-like expression that mirrors, if you want, the CHSH-like structure of omega. And well, it is not difficult to show that this is strictly positive for all vectors in the blunt square. Note that the strict inequality sign, because we cut off the corners. And okay, this is a very long computation, but you can show that it's smaller than 0 or equal to 0 on omega. So this is not in the minimal tensor product. Okay, just very quickly, conclusions. local non-classicality, which is the existence of superpositions, and global entangleability are very intimately linked. And this connection is not an accidental feature of quantum formalism, but it has really a universal feature, a universal nature, right? So it's really a universal feature of GPTs. And this mathematical problem that stems from this was 50 years old. So the works of Namioka, Phelps, and Barker, among others, but they had a completely different motivation. So I'd like to highlight some quantitative open questions. One is to give a quantitative statement analogous to ours, which is to find basically, I don't know, a measure of non-classicality and a measure of entangleability such that you can say, if my cones are such and such non-classical, I can give a lower bound on how much they are entanglable. Okay? It's just an example of a possible relation. And the other phenomenon, the other open question is about other phenomena. So what about non-locality? Is it also a universal property of GPTs in this sense? So this is, of course, a vast program, as somebody would have said. And with that, I leave you and I thank you for tuning in.
Thank you very much for this nice talk and the very aesthetic results. So yeah, there are some, so there's one question by Andreas Winter, which maybe goes in the direction of your open question 5. So obvious and probably expected question. You show that in the product of non-classical theories, there are entangled states. Can you strengthen that to the violation of a Bell inequality, perhaps CHSH? Maybe at least the violation of a steering inequality. I think the latter is what Namioka Phelps gives you.
Yeah, okay. So that's a very interesting question. It's not that I have looked super hard into this. So it seems to me that, so you see this fact that we use the kind of our inequality has a, like the separation is basically infinitesimal, right? Because here you have a strict inequality and here you can just show that it's barely violated. So this somehow seems to stand in the way to establish a violation of the CHSH. But yeah, you are right. I mean, probably you have a better chance with a steering inequality, but this I haven't looked into this. But this is a very good question. Yes. I don't know. Maybe exactly. I mean, I don't know. I don't really know. It could be.
Okay. I also have another question. So now, I mean, what you've shown is that there is universally these universal entangled states that somehow are in every pair of non-classical cones. Do you know how these states look like for the PSD cones? I guess that we most
yes, we do, and that's slightly disappointing because it turns out they are not positive. They're not positive definite. So they are in the maximal tensor product, but they are not only they are not separable, but they are not even positive definite. So somehow, yes, it would be. So that's also one. I mean, it would be very nice to have a universal construction that gives you something that you recognize in quantum theory. And yeah, it's not for this case. So that's why the proof is super sophisticated to me, especially in the convex geometry sector. But it still lacks something on the physical side. I agree.
Okay. Then. Yeah, okay, maybe one clarification, like in dimension 2, minimal and maximal tensor product of cones are known to be always the same. That's what Cecilia asks.
In dimension 2, if you mean, yeah, exactly. I mean, dimension 2, basically, yes, because, I mean, in dimension 2, I mean, the only cones are classical, right? I mean, the only cones are kind of sectors of the plane. So basically, I mean, the state space is a straight line. So in particular, it's a simplex. So if any of the two cones is two-dimensional, the problem trivializes. So the first non-trivial case indeed is for three-dimensional cones. Yeah, thanks for the question. I didn't say it explicitly. Okay, then thanks again for the nice talk. And everybody. So I want to just know, I mean, yeah, make sure that so you know that there's more discussion. You can ask more questions to Ludovico in the roundtable at I think 12:30.